Okay, so this is 6.2 homework, basic concepts of probability. We want to use our answers to homework, and this should say 6.1 to answer 1 and 2. So two ordinary dice are rolled. Make sure to describe the sample space and the event space. So over here, you can look on 6.1, just copy these down. So I have 1, comma 1, then I have 2, comma 1, and then I have 3, comma 1, and I have 4, comma 1, 5, comma 1, 6, comma 1. And you just keep writing these down. So then I have next, let's put commas after each of these because we're going to list all of them. And this is a set of things. And so then I have 1, comma 2, 2, comma 2, 3, comma 2, 4, comma 2, 5, comma 2, and 6, comma 2. Again, commas after all these because we're listing them. And you just keep on going. So 1, comma 3, 2, comma 3, 3, comma 3, 4, comma 3, 5, comma 3, 6, comma 3, and commas after each of these. 1, comma 4, 2, comma 4, 3, comma 4, 4, comma 4, 5, comma 4, and then finally 6 here, comma 4, and then comma again after each of these. And then we have 1, comma 5, 2, comma 5, 3, comma 5, 4, comma 5, 5, comma 5, and then what's this last one? 6, comma 5. And then commas here, 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 and here. And finally the last one, 1, comma 6, 2, comma 6, 3, comma 6, 4, comma 6, 5, comma 6, and finally 6, comma 6. Commas after each of these except for the last one because the set's done. All right, so you just list all the different possible outcomes. And then we want to figure out the probabilities of these certain events. So in part A, it says determine the probability that a 3 is rolled. All right, so up here, what I'm going to do is I'm going to use a different color, and I'm going to look for a 3. And so, I have a 3 here. Of course, I have a 3 there. And I have a bunch of 3s here. And so here are a bunch of 3s. And then, of course, I have a 3 here, a 3 here, and a 3 there. And so I can copy all these down. So here are my events. So I have 3, comma 1, comma, 3, comma 2, comma, and then I have all of these 1, comma 3, 2, comma 3, 3, comma 3, 4, comma 3, 5, comma 3, 6, comma 3, and then finally with these last 3, 3, comma 4, 3, comma 5, and 3, comma 6. All right, the probability that E occurs, well, it's just equal to the number of things in E divided by the number of things in S. And so this is equal to, just count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 things that have a 3 in them. And then divided by the number of things in S, which was 36. Right, so if I roll 2 die 36 times, I would expect that 11 times I would see a 3 rolled. We can also write the percentage of this. So or on my calculator, I can just take 11 divided by 36, and that's going to be equal to about 31%. So, or about 31% of the time. Okay, the next one, determine the probability that 2 die add up to 7. Okay, so let's choose a different color here. Let's choose blue. And you go through these and you add the die, and you'll see that the first case of a 7 is 6 and 1. And then over here, it's only 5 and 2. You'll see here 4 and 3. You'll have 3 and 4. You'll have 2 and 5. And you'll have 1 and 6. And so I can list my event space, and I just copy down those in blue. So I have 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, and then the last one, 1, 6. And to figure out the probability of this event occurring, I take the number of things in E, and I just divide by the number of things in S. So I have 1, 2, 3, 4, 5, 6 things in E. Of course, I have 36 things in S, and so that's just 1 divided by 6. And I can figure out the percentage, 1 divided by 6, right? Or this is about 17%. So now what does this mean? This means if I roll the 2 die 6 times, I would expect at least one time out of those 6, I'd throw a pair that add to 7. Now, will it happen if I do it exactly 6 times? Probably not, right? But if I do it, let's say 100,000 times, I'm pretty sure that I get about 17% of those times, those pair will add up to 7. All right, and number 2. All right, a penny is tossed 4 times. Make sure to describe the sample space and the event space. Again, you're just supposed to look at 6.1 and copy them all down. So I'm just going to look at my 6.1 and copy them down. So I have HH, HH. I have HH, HT, HH, TH, HH, TT, HT, HH, HTT, H, H, T, T, T. Let's make that H better. And then up here I have H, T, H, T. And I'll start a new row. And then I have T, H, 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 T, H, H, T, T, H, T, H, T, H, T, 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 H, H. And then T, T, H, T, and then T, 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 H, and finally, last one, T, 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 T. All right, let's count them up just to make sure I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so that looks good. And I want to determine the following probabilities. So to determine the probability that at most 2 heads are tossed. So up here, right, at most 2 heads are tossed, which means no more than 2. So that has 4, so that's no good. 3, that's no good. 3, that's no good. This one's okay. So that has 2. This has 3, no good. This one's okay. This has 2, so at most 2. This has 1, so that satisfies. It's at most 2. This has 2, so it's okay. So we'll keep it. This has 3, so no good. This one has 2, so it's good. This one has 2, so it's good. This one has 1, so it's good. This one has 2, so it's good. This one has 1, so it's good. This one has 1, so it's good. And this has none, so it's also good, right? At most 2. If it has none, then it satisfies the condition of at most 2. And so what I can do is list these then. So down here, I'll just list these that I found. So HH, TT, HTTH, HTTT. Just go in order. HT, next row, TH, HT, TH, 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 TT, TTHH, TTHT, and TTTH, and finally all T's. T, 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 T. All right, so there's a set. The probability that this event occurs, well, you just count the number of things up in E, divide by the number of things in S. So in this case, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I have 11 things. So 11 divided by the total number of things in S is 16. So 11 over 16, or I can do this on my calculator. So 11 divided by 16 is what percentage? About 69% of the time. So 69% of the time, I'll draw at most 2 heads, or toss at most 2 heads. All right, determine the probability that there's exactly 3 tails are tossed. So let's look at this one. Let's do this one in blue. All right, so I'm looking for exactly 3 tails. So 0, 1 tail, 1 tail, 2 tail, 1 tail, 2 tail. Here's 3. There's 1. That has 2 tails, 1 tail, 2 tail, 2 tail. This has 3 tails. 2 tails. This has 3 tails. This is TTH, and that's a T there. This has 3 tails. And the last one has 4 tails, so not exactly 3. So I can copy these down. So what I get is H, T, T, T. Then I have T, H, T, T. And then I have T, T, H, T. And then I have finally, oops, I skipped one here. Which one did I miss? My T, T, H, T. Oh, 3. I missed that one. So that last one. T, 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 H. There it is. So this is equal to the probability that E occurs is E, the number of things in E, divided by the number of things in S. And so there's 4 things in E. There's 36 things. Oops, not 36. That's the last problem. There's 16 things. There's 16 things in S. So this is 4 divided by 16, which equals 1/4. Or this one I know in my head, I can do this one in my head, it's 25%. So 25% of the time I will roll, or I'll toss exactly 3 heads. All right, let's look at the next page. All right, so on the next page, we want to consider 52 deck of cards. And we're going to determine the probability that a card is a 4. All right, so up here, let's think, okay, we have 52 cards, and how many things do we have in our event space? So our event, let's just say E, is equal to all 4s, right? So you have, basically, you can say, you know, a 4 of hearts, a 4 of diamonds, a 4 of clubs, and a 4 of, and then we might do my spades, so spades. And then S, of course, is all 52 cards. So on this one, if I want to find the probability of E, okay, what is this going to equal? It's going to equal the number of things in E divided by the number of things in S. And so you have 4 things in E divided by 52 things. And so this is equal to, well, the 2's cancel because they're even. And then the 2's cancel again. So 1 over 13. Right? Or if you want on your calculator, you can figure this out. 1 over 13 is equal to about 7.7%. So let's keep it with 1 decimal place, so 7.7%. But this is my answer, 1 divided by 13. So if I draw 13 cards, I would expect one of those would be a 4. Will it happen if I draw exactly 13 cards? Maybe, maybe not. But the idea is if you keep on drawing, okay, and replacing, basically 7.7% of the time, you'll pull out a 4. Right, determine the probability that the top card is a heart. All right, so now my event space, all right, are all the heart cards. And so they're actually, if you think about this, there's 52 cards in a deck, and there are 4 suits. So you take 52 divided by 4, and you'll see, oh yeah, there's 13 hearts. All right, so 13 different hearts. All right, I don't want to list all of them. And then my sample space is still equal to the set of all 52 cards. All right, these are supposed to be curly brackets. And so what I want to find is the probability that I draw a heart, which is equal to the number of things in E divided by the number of things in S. And so there are 13 possible heart cards divided by the total number of cards, which is 52. And this will actually simplify to 1/4 because 13 goes into 52 4 times, right? Or you could say 25%, which is somewhat obvious when you think about it. If there's only 4 suits, right? 25% of the time, you're going to draw a heart. All right, let's look at the next one, part C. So on this one, it says, if you deal out 5 cards, determine the probability that you deal a royal flush. Okay, so E is equal to all the possible royal flushes. So these are all the royal flushes. And a royal flush is an ace, king, queen, jack, and 10, all the same suit. Right? So really, how many royal flushes do you have? Well, it's just the number of suits. So you have the royal flush with the hearts. You have the royal flush with the diamond suit. You have the royal flush with the clubs suit. And you have the royal flush with the spades suit. And then again, S is still all 52 cards. And so the probability, oops, this one's going to change a little bit. So here I have to be a little bit careful. All right, it's not just the 52 cards. All right, E's fine, but this is going to be a lot more than 52. Right, if there are only 52 hands in poker, poker would not be a very interesting game. So this is all 5-card hands. All right, so on this one, we're going to have to do a little bit of thinking to count, how many things are in S. Our goal here is to figure out basically the probability of E, which equals the number of things in E divided by the number of things in S. Now, the number of things in E is easy. There's just 4 royal flushes. So it's 4 divided by. But to count all the 5-card hands, remember, how do we do this? Well, we have 5 spots. We get 52 choices for my first spot, 51 for the second, 50 for the third, 49 for the fourth, and 48 for the fifth. Okay. But we've counted some things too many times. If I get, let's say 2, 3, 4, 5, 6 of hearts, if I just put a 2 here and a 3 there, I don't want to count that as a different hand. But right here, how I'm counting it as a different hand. So the idea is then I have to divide out. Right, after I do this multiplication, I divide out the different ways there are to rearrange 5 given cards, which is 5 times 4 times 3 times 2 times 1. So on my calculator, I can do this. So my calculator, I take 52 times 51 times 50 times 49 times 48, and then divide by left parenthesis 5 times 4 times 3 times 2 times 1, in parenthesis, hit enter, and I get out this number, 2,598,960 possible hands. So down here, right, what do I have? Well, down here I write this number, 4 divided by 2,598,960. And this can actually be reduced because 4 goes into this. So if I divide this by 4, you'll see I actually get out 1 divided by 649,740. All right, so if I deal out 649,740 hands, I would expect just one of those to be a royal flush. You can crunch the percentage, but it's going to be so small that we'll probably, let's just leave it as a fraction. But here's the percentage. It's 1.5390, blah, 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 e to the -6, which means move that decimal place over 6 places to the left, All right, then you create a percentage out of it, and it's still 0.00001, I'd say, percent. So it's very small. So let's just leave it as a fraction, 1 divided by 649,740. All right. If you deal out 5 cards, determine the probability that you deal 4 aces. Okay, so our event is that we have 4 aces. And so what we have to do here is we have to count, in a sense, the hands with 4 aces. Okay, and still S is equal to all 5 card hands. And we've already counted that, so we can just use our previous work for that one. All right, so to count the hands with 4 aces, okay, the idea is you have 4 aces, so we can just put, with 5 cards, we can just put an ace here, so this might be like the ace of hearts. That's great. All right, let's do the ace of diamonds, ace of clubs, and finally the ace of, spades. And then here we have how many choices for this last spot. Well, we already have our 4 aces, so, well, we used 1 card, 2 card, 3 card, 4 card. There's 52 cards possible, right? Oops, all 5 card hands. That should be all 5 card hands. Right, but there's 52 cards possible. If you've used 4 of them, how many do you have left? Well, 48. All right, so the number of things in E are just 48. There are 48 different hands that include 4 aces. The 4 aces are already there, and so you just have 48 possibilities for the 5th card in a sense. And so the probability that E occurs is equal to the number of things in E divided by the number of things in S, and that's equal to 48, right, divided by, right, the number of things in S was above here, 2,598,960. So on your calculator, you can check if this is can be reduced. You can do this division. 598,960. All right, and if you want, you should be able to hit math, convert it back into fraction. Oh, it won't work. Well, the number's too small. All right, but if you notice, this 48 goes into this number, right? So the calculator let us down here. But you can actually see, if you do this, you want to check and see, does 48 go into 2598960? And it does. So this actually, the 48s will cancel top and bottom and get 1 over 54,145, which gives you a better feel. Okay, so if you deal out 54,145 hands, you would expect that just one of those hands will be 4 aces. All right, let's finish this up and do this last one, and then we'll be done with this assignment. Okay, so on number 4, what do we have? It says, suppose you put 13 names, Marky, Ricky, Danny, Terry, Mikey, Davey, Timmy, Tommy, Joey, Robbie, Johnny, Brian, and Will, into a hat and draw 2 names. If you replace the names after each draw, determine the probability of drawing Will's name. All right, so what we have is an event space and a sample space, and we're making 2 drawings, so let's do both of these. In a sample space, let's just count the number of things in S. Right. The idea is you're making 2 drawings, and in part A, you're going to replace the names. All right, so there's 13 names total, so the first one you have 13. Right. Then for the next one, since you replaced, you also have 13. All right, so this is basically 13 times 13, which is 169. So there's 169 things in our sample space. And our event space, right, remember our event is drawing Will's name in one of the spots. And so the way we're going to count this is we're going to count it like we're going to pretend like we drew Will's name in the first spot. So we say, oh, okay, pretend like you drew Will's name in the first spot. Well, how many names can you put here? And we won't count Will's name again. So again, you could have Will, you could have Will and Marky, Will Ricky, Will Danny, Will Terry, Will Mikey, Will Davey, Will Timmy, Will Tommy, Will Joey, Will Rob, Will Johnny, Will Brian. So there's 12 of them. Right? So you count all 12. Plus, instead of drawing Will's name in the first spot, you could have drawn it in the second. And again, you have 12 choices for the first if you exclude that Will again. So, you could have Marky Will, Ricky Will, Danny Will, Terry Will, and so on, all the way up to Brian Will. Then plus, the one case we haven't counted is when we draw Will in the first spot, then replace and draw Will in the second. And so total, we have 12 plus 1, which is 25. And so the probability of drawing Will's name is equal to the number of things in E divided by the number of things in S, which is 25 divided by 169. And we can put this into our calculator. So 25 divided by 169 is equal to, or about 14, and I'll just round this to one decimal place, 0.8% of the time. But this is my answer. All right, so if I do this drawing 169 times, I expect 25 times I will draw Will's name. All right, so the next piece, it says, now if you do not replace the names after each draw, determine the probability of drawing Will's name. Okay. So the number of things in our sample space is going to change. Why is it going to change? Because we're not replacing. So things like Marky Marky can't happen. And so what we have, again, is 2 spots. We have 13 choices for the first spot. And then how many choices do we have for the second? Not 13, but 12. And you can take 13 times 12 on your calculator, and you'll see that's equal to 156. So now we have 156 things in our sample space. So that certainly is going to change this denominator, 169. And then the number of things in E is going to change slightly too. So again, we'll count these by cases. So we'll say, all right, let's imagine that we drew Will's name in the first spot. Then what can we draw on the second spot? Well, we already drew Will's name, so we just have these 12 names left. Again, we're not replacing, so we really only have 12 names left. Plus, instead of drawing Will's name on the first spot, we could draw it in the second spot. And again, we have 12 names that could go in the first spot. We no longer have this 1-1 case because we're not replacing Will's name. So it can't occur. So this gives us just 24 possible things for our event space. And so now the probability that we'll draw Will's name, if we do not replace, is equal to 24 over 156. And again, we can actually simplify, right? So this is equal to, we can go down, let's see, just by 2. So 12, and then this would be, 78. Then we can go down by 2's again, so that would be 6 divided by, 39. Oh, we keep going down by 3's, okay? So this would be 2 divided by, use 13. Right? So 2 divided by 13. Or, to figure out the percentage, up here we can take 2 divided by 13 and hit enter, and we get about 15.4% of the time. Right? But this is our answer right here, 2 divided by 13. All right, so this is somewhat interesting. You can see that there's we're more likely to draw Will's name actually if we do not replace it versus replacing it.